Thanks, Christy, and thanks to the organizers for hosting me here in what I think will be yet another exciting CIDER. The lecture today is trying to cover some of the basics in terms of our understanding how subduction features in the global mantle convection system. And I'll be covering some of the largest scales, and for sure, this lecture will not even attempt to cover all the basics. And I've tried to work around some of the presentations that we'll hear later in the week and later today. And so, for example, Magali will be talking about the effect of phase transitions, and Peter will later be talking about how to compute detailed thermal models of subduction zones, for example. But in general, the idea here is we have our planet, and where we know the internal structure, we know what's happening in the oceanic domains, as illustrated here by the seafloor age distributions, and we want to know how does this system dynamically evolve, and how does the system link to mantle convection is expressed here by subducting cold thermal boundary layers in this 3D spherical computation. And what is a challenge right now is to do this not just for the recent time, but for longer time scales, such that we can factor in the memory of planetary evolution that is preserved in the continents, as indicated here by these geological units, over billions of years rather than hundreds of millions of years. But I'll be focusing on our sort of fundamental approaches to the oceanic system here for the most part. I'm going to be talking a little bit about plate driving forces, some of the basic fluid dynamics that can be used as rules to tell us about why things are moving and how fast things are moving, as opposed to sort of the detailed expressions assuming known velocities, known kinematics. I'll be focusing some on global scales first. It's pretty exciting. Some of the people who made the most fundamental contributions on global and regional modeling are in the audience today. In the end, I'm going to come back to sort of this idea of conveyor belts just because it's somewhat amusing and it provides a link to the continental domain. I'll be commenting some on outstanding issues that remain in these fields, but I'll also not try to give you a laundry list of things that I think are exciting in subduction zone science. For example, there are groups, including the folks at ETH, with Yolanda van Dinter and Luc Lavier at UT, who are trying to bridge the timescales between tectonic and earthquake cycles. That's exciting. It's exciting to think about linking in the volcanic system with subduction zones and so on. So there are numerous emerging fields right now that I will not have time to talk about. So I'll try to give you some feeling for the rules that govern sort of the general dynamics of subduction zones. Now, overall, it's somewhat a commonplace and almost too simple a statement, but I think it's worthwhile to keep in mind that when we're talking about subduction, we're talking about the cold surface thermal boundary layer of a convective system. And any attempt to divvy things up in like bottom up or top down tectonics is trying to sort of build a straw man out of a system that can really be only understood in terms of the overall heat engine of the Earth. Well, when we look at the simplest convective system, a Rayleigh-Bénard system that's heated from below, the hot upwellings and the cold downwellings are exactly symmetrical if there are no variations in viscosity, right? And so the question about subduction would be as important as the question about plumes. This is not quite how the mantle works, and the mantle has a number of effects at work that break the symmetry between downwellings and upwellings. Here's a rendering. This is a computation by Alan McNamara, a very simple convection computation that misses a lot of aspects of the Earth, such as three-dimensionality, but that can serve to illustrate some of the fundamentals. The downwellings here, the blue things, which you may associate with subduction zones, if you will, do not look the same as the upwellings. There's a number of reasons for this. In this particular model, there's two reasons. One is that there is a viscosity that depends on temperature. And that makes the cold downwellings wider because the local dynamics are different, and the hot outwellings are relatively thinner. There's also an increase in viscosity when you go from the upper mantle to the lower mantle, and that again changes the dynamics because it makes the local vigor of convection that is described by the Rayleigh number here slightly lower than on the top, meaning the time dependence is slower. That could serve, for example, to anchor these upwellings and make them relatively more sluggish. But a number of points I want to make here, in particular, that if you identify these cold downwellings with subduction zones, then you immediately realize that they are time-dependent features, right? Subduction zones move about. The trench, the place where the subduction zone goes into the mantle, changes its position with respect to the lower mantle, and there's all kinds of irregularities, for example, in the plate speeds. Right? Other factors that will break the symmetry and affect the symmetry is the partitioning between internal and bottom heating, something I'm going to come back to later, and also, of course, fractionation. Right? The Earth is not a thermal convecting system, it's a thermochemical system. And fractionation, melting of material, matters in a number of ways. It leads to the formation of continents, which are these floaters on top that are not subducting, obviously. And also you have effects such as the formation of the continental crust and the relative densities of the depleted residuum that will make subduction work differently when it comes to the density than the simple thermal system. But it's important to keep this in mind that you'll lose a lot if you forget about this sort of background dynamic system. And we can then take the system and explore different components of it. Not because the reduction itself is a means to an end, but because it can give us a feeling for some of the physical processes that are going on. The most fundamental one, and sort of the biggest achievement of geodynamics really, is to realize that the cooling of a hot layer that is advected sideways from the spreading center is a good model to describe the oceanic lithosphere, in particular the flattening of the seafloor if you go from the spreading center to the sides. The equation that describes this behavior is this one here, where we have a combination of the heat flow being given by a gradient of temperature. If we then ask, well, if we have a control volume where heat flows in, flows out, we can integrate over this and we can rewrite the equation, and we find that the temperature change is given by an important parameter, the diffusivity, times that divergence here, that second derivative of temperature in this particular case in one dimension with depth. And so if we solve this equation, then we find that the temperature with space here, which is really a proxy for time, and depth is given by an error function, not that important, and then a depth times the scale length here. Right? This is one of the few nonlinear partial differential equations that you can solve analytically. You solve it by what is called a similarity variable, but really what this is saying is that every length scale is only meaningful when related to a length scale that is given by diffusivity times time and square root thereof. And that follows from the dimension of the diffusivity length square over time, if you want, and it's an important feature of any diffusive process. Right? And so this tells us the thickness of the thermal lithosphere. If we apply isostasy to it, it tells us the depth of the seafloor. But also we had already discussions about the temperature distribution along a slab that's diving into the mantle. Then the diffusive part, the transport without any advection, will always be governed by this sort of length scale, or if you turn it around, by a time scale that is given by the square of the length scale. Okay, so this is an important thing to keep in mind if you have transport of heat without flow. Now, we can use this information about the basic structure of the oceanic lithosphere to come back to this question as to, well, what are the driving forces of plate tectonics? And that's another exercise in reduction where we take parts of the thermal convection system and we integrate over it, and we ask, well, what about this thing here, the force of the plate that's thickening, typically called ridge push? What about slab pull? What about gravitational potential energy that I won't be talking about much today? And so if we take the boundary layer apply this theory that's basically, it's just an application of diffusion, half-space cooling. How long does it take for the boundary layer to penetrate? We can compute the pressure within the plate, and we can integrate over this, apply isostasy, and we get an equation for the force that corresponds to the lithospheric thickening, so-called ridge push. And it has an equation here that's to do with isostasy, depends on the velocity, gravitational acceleration, density, contrast, and then we have to integrate along the plate. We can also then take this boundary layer and ask, well, what happens when the boundary layer actually goes down? And if we integrate over that part of the boundary layer, just this thing here, where we know what comes in here from the half-space cooling, we get another equation that tells us the force expressed as the temperature difference here between the surface and the mantle, and the thermal expansivity, and the length extent, and the depth here of the slab, and then again we have this equation here that's to do with diffusion, and that gives us slab pull. All right? And so if we then compute, and this is a basic exercise everybody should do, the relative magnitudes of these forces, we find that slab pull is about a factor 10 larger expressed in force per length than ridge push. Right? And this is one of the reasons why we worry about slab pull, because if you're interested in any sort of tectonic activity, the first guess should really be slab pull, right? And this is something that sometimes gets forgotten. If you isolate parts of the system, you ask, well, how does a mountain form? Well, this moves that way, this moves that way, but if you're interested in the forces, really slab pull is a good first guess. And this whole idea of a thermal boundary layer is also reflected in seismological observations, and to some extent, it's really a major achievement, but then there are also still questions about the general nature of the thermal boundary layer and if things are really as simple or not, but it gives you still a first good idea of what's happening. Right, so now let's apply some of this knowledge, and let's push a little bit further and look at the kind of experiments that Earth has set up for us right now. Right? And so we can look at the present-day plate motions, which are illustrated here in some reference frame where the background colors are showing you the amplitudes of motions, and we can ask, well, what drives these plate motions? And given our ideas about slab pull, is this a useful way to explain the several different experiments that you can think of that are being represented here by large-scale plate motions? And you can see immediately, for example, that the plates that are oceanic in nature move much faster than the plates that have a lot of continental area. Usually those places are also the plates that have slabs attached. And you can see a lot of funky things, such as the really fast rollback motion here of Tonga, and a bunch of other interesting sort of intraplate scenarios. We have these little microplates that are spinning and so on. But in general, there's like one realization of an ensemble of different behaviors given the same sort of thermal state, because we're talking about the present day. And so, yes?
So what is the spreading line reference frame?
This is the best reference frame because we've proposed it in 2015. We can come back to that later. It's just, for our purposes here, it's one absolute plate motion reference frame. And the important thing to realize is that if we measure plate motions with spreading, with C4 spreading, with magnetic anomalies, with GPS, or with polar wanderpath, there's no absolute reference frame, right? All we can ever say is the rate of one plate with respect to another. And then we need to make choices, and you can make choices such as holding one plate fixed. In this particular reference frame, Antarctica is naturally almost fixed. You can say that the surface of the Earth should not spin in a wholesale fashion. That's a no net rotation reference frame. Or you can pick something else, like fixity of hotspots, which will lead to a hotspot reference frame, and this thing leads to an alignment of absolute plate motions with relative spreading direction, and it also tends to match azimuthal anisotropy very well, and it seems to have a pleasingly agreement with the amount of net rotation that is generated by geodynamic models. That's why we think it's a useful sort of one-size-fits-all reference frame.
Is there much difference from the no net rotation?
It does have a net rotation that is somewhere halfway between 0, which is no net rotation, and the hotspot reference frames. So it has a bit of net rotation, and you can see that here, and we're going to come back to that. I'm going to illustrate that later.
Excuse me?
Yeah.
Why there are red bands on the north and south of Pacific plate?
These things, that's just the color scale here, where red is a little bit slower than white. White is the fastest color. And you're looking at a rigid motion on a sphere, right? So for the Pacific plate, the pole, the Euler pole, is sort of like that. And you're looking sideways at the plate spinning around the Euler pole, which happens when you have a fast plate, right, where the pulling is from the sides. And so you can see here, for example, that Africa has this curvature because the pole is fairly close to the plate, right? And here you can see a strong gradient because the pole is actually inside the plate. People have worked on, you know, the systematics of that. But that's why I like this color, because it gives you a feeling that you're on the surface of the sphere, right? And even for rigid plate motion, you get quite strong gradients in the velocities. And so we have this set of experiments. And without any computations, any fluid dynamics, we can just go out and do correlations. We can just explore all the different data that is being generated by plate tectonics, and that was done by a number of people, including Boyd Forsyth and Ueda. And what they did is they looked at absolute plate speeds and looked at a bunch of different things you can measure from these plate tectonic models. And then when you compute correlations, it was done here, as it was visualized here by Scott King, you find that the effective subduction zone boundary length, how many slabs are attached, really has a nice positive correlation with plate velocity. So slab pull is pretty important. Now it's somewhat more complicated because if you look, for example, at the total continental area, then that has a fairly strong negative correlation, which would indicate, say, if there's a continental keel, some strong viscous thing that would slow things down. And more than that, turns out then there's this anti-correlation between continental area and effective subduction zone boundary. Right? So you already see from this analysis that it's hard to tease out systematics because there are covariances between these different parameters. They're not independent, right? And nature wasn't nice enough to set us up with an experiment where we're just varying one parameter, right? So it's a little bit more complicated. Pardon me? The question is, what does it mean, effective subduction zone boundary? It's basically normalized per like some total length, how much of the boundaries of the plate are attached to a slab. Right? It's just some way without doing any math to figure out the importance of slab pull.
Okay, thanks.
Right? And so because this is kind of complicated and a little bit wishy-washy, this is why we resort to fluid dynamics. And I want to talk a little bit about this because you can get some insights from these equations that are helpful even if you're not solving the equations. And so when we talk about Mantle convection, we can start with the circulation system, just with fluid flow, assuming we know where the density anomalies are. What we then have is a force balance, also called conservation of momentum because it sounds fancier, where we have summed up gradients of the stress tensor, and those are balanced by body forces, and typically those body forces here will be given by density anomalies times gravity, some sort of buoyancy. That is true for any sort of material. And it's just a force balance, a static force balance. There's no inertia in here because, as it turns out, flow is so sluggish we don't have to worry about this. The Prandtl number is infinite. Now then, if we assume material behavior, we can, for instance, treat the mantle as an incompressible Newtonian fluid. Incompressibility then says that the divergence of the velocity is 0. That gives us conservation of mass. And we can then express the constitutive law, the stress tensor, as a function of the kinematics, the sort of mixed derivative, the antisymmetric derivatives of the velocities, which are called the strain rate tensor. And so we can write the stress as a dynamic pressure plus Newtonian viscosity times the strain rate. Right? So for all intensive purposes, the shearing that you're doing is balanced. The force needed to shear depends linearly on the strain rate times the viscosity. That's one simplified assumption. If we plug that in, we end up with this equation here that tells us that for any sort of flow that's Newtonian, the viscous drag, viscosity times strain rate, some sort of gradient in strain rates, is balanced by the dynamic pressure gradient and the buoyancy force. Okay, so whatever you're asking about subduction, this equation has to hold. Right? If you want to move things, you'll exert, you somehow make viscous drag, and you can do that by putting in a density anomaly, or you can do that by putting in a pressure gradient. Right? So it comes then, geodynamics comes down to guessing the pressure gradients, or knowing the pressure gradients, and knowing the density distributions. Yeah.
The Coriolis force is actually much more important than the neglected inertia, right?
Yes.
So it would be probably maybe 10 to the minus 15 as opposed to 10 to the minus 25.
Correct. Yes. Yes. And I know that because you made that comment a couple of years ago. And there's a really nice paper in '66 that works this all out in an appendix, and I forget the author. No, it's true. So you have to be more worried about the spinning of the Earth than the Prandtl number. And the Prandtl number, incidentally, is the ratio of diffusion of momentum to diffusion of heat. And that means if you change plate motion, say at the surface of the Earth, the core metal boundary will immediately know where things are moving at the surface. So the system is sort of interconnected. There's no propagation of some inertial wave.
I just have a question. The bottom one is, I guess, is only valid for constant viscosity. So
Right.
if the viscosity is a function of like depth, so how different this equation will be, and what's the implication?
It'll just make this equation more difficult to solve, and you'll have to solve it numerically, and it's just going to look more complicated. But there's no real issue. You got to factor it in, right? And it's a more complicated expression that talks about how the gradients and velocities talk to the stresses. There's no fundamental difference. Some of the solutions, if the viscosity just changes with depth, are still analytical, semi-analytical for layers, right? But if you have lateral viscosity variations, you need to use numerical methods. But it's not a problem. All right, if you don't like these equations, here's one thing that you should take away from today's lecture, if you haven't worked through this in fluid dynamics before, and that's the scale in terms of velocity that is set for all sorts of density-driven flow, right? As opposed to the flow where you're pushing. We don't want to worry so much about things where you're pushing today. And so what you can do is you can consider a sphere, and you can figure out that the drag force due to this viscous deformation should be balanced by the gravitational force. Drag force is area times stress, and then you plug in the constitutive law, strain rate times viscosity. The strain rate, you can guess that it should be given by a velocity over the radius of the sphere, because there's no other length scale. And then you can work out that the density contrast times the gravitational acceleration times the volume gives you this force, and you can find this equation for the Stokes velocity. If you never worked this out, please do it. It's trivial once you realize those relationships. Okay, and this says that any object of radius a will have a velocity that's given by delta rho over the viscosity of the ambient medium. And that equation is correct up to about a factor order of magnitude c, and you can work out that this c depends on the ratio of the viscosity of the sphere to the viscosity of the mantle, and you can then, for instance, if the viscosity of the sphere is super high, if it's a cannonball, this goes super high, so it's 2/6, 1/3, right? So this thing is 1/3. But it doesn't really matter that much. It's one of the odd things about Stokes velocities. Now then you might also go like, well, this is a sphere, right? The slab is like this long thing, or what have you. And it also turns out that changes in shape, right? If a needle falls like this, or like that, again, give you only a factor of 2, 3 difference in flow. This is one of the odd things about Stokes. What's also interesting is that now coming back to this problem of how fast does the slab heat up, right? I already mentioned that the diffusive timescales will be given by the square root of diffusivity times time, or the length scales, turn it around. And then there's the advective part. Right? If you're worried about advection and diffusion, those two are the main players, are the players in convection. And so if we have transport, moving things around, we're shoving in the slab with some velocity, then we might want to know, well, how important is that transport compared to diffusion? One way to answer this is by defining another number, the Peckley number, which is the ratio of the diffusive to the convective timescale. If the Peckley number is large, then advection dominates. You will have little diffusion. The slab will lose only a little bit of heat, and vice versa. Now, the diffusive timescale, we already know. It's a length scale squared divided by the diffusivity, just like for the thermal boundary layer, just turned around. And then what is the convective timescale? Well, we can define the convective timescale based on the Stokes velocity, right? If this is our slablet sinker, we're asking, well, if it's driven by thermal anomalies, how quickly will it go down as opposed to diffusing away? We can plug in a thermal buoyancy, temperature difference, expansivity, rho 0, and then the Peckley number turns into the Rayleigh number, which is the number that describes the convective vigor of the system I showed you earlier. Right? So there's a link here between the diffusion and the advection, and you can come up with the Rayleigh number this way, which is kind of nifty. And you got to plug in the length, the height of the box, rather than the radius for this to work. Important thing here, though, to take away, velocities go with density anomalies divided by the viscosity. So if you're asking, well, what if this phase transition changes the compositional buoyancy? Is the slab still going to sink? Well, you work out the density anomaly, and you work out the viscosity, you guess the viscosity, that gives you a time scale, and then you can use the Peckley number to see if things will diffuse away or subduct. But this is the kind of stuff I want you to take away. If you look at a stress-related quantity, stress goes with viscosity times strain rate. The strain rate has the velocity times over a length scale. And so if you plug that back in, you find that stress will go by density anomaly divided by a length scale only. So the viscosity dropped out. What this means is that if you increase the viscosity somewhere, the strain rates are going to go down, but you multiply it with a larger number such that the stresses are the same. Stresses you might care about because you're looking at earthquakes. You might care about because you're looking at dynamic topography, because you can show that the deflection of the surface goes to first order with the stress. Right? So any density-driven flow, it's the density anomaly that governs the stress quantities, and it's the density anomaly divided by the viscosity that governs the velocity. Right? And this is the foundation of some of the tricks that we use to invert for both. Right? We measure something that tells us about one thing, gives us the density anomaly, and for instance, the plate velocity, then give you this other unknown. So let's do this. Let's look at plate motions and actually compute mantle flow. Going back to Hager and O'Connell on a sphere. Now for this, we use the equations I just discussed. We have the force balance, and we look, for example, at non-dimensionalized temperature times the Rayleigh number, which falls out if you non-dimensionalize the system. That gives you the thermal buoyancy. We again use some constitutive law, and as I mentioned earlier, if viscosity only changes with depth, we can solve this in less than a second in terms of its global flow. If we have lateral viscosity variations, as I mentioned earlier, here written somewhat sloppily, if we have a viscosity that depends on stress, temperature, grain size, water content, path, strain, for example, we need to use finite element methods. We can run these computations, not necessarily me, but the community can, at resolutions down to about 1 kilometer or so on 500 CPUs on a couple of hours or days. So this is entirely feasible. And to some extent, particularly for the circulation problem, if you know where the density anomalies are, we're not technology limited to make any sorts of predictions. We are limited as to knowing what the densities are or the viscosities are. So how do we guess a density for the mantle to ask if slab pull is indeed driving the plates? One thing we can do, going back to Hager in '84, is we can look at the Wadati-Benioff zone. Wadati-Benioff zone? That just sounds stupid. The Wadati-Benioff zones. It's just like the Cordillera. Sounds better, you know? Cordillera. So, we know where the seismicity is from the earthquakes. So we say, well, there's cold stuff going down. We make up we take the thermal boundary layer that we just worked out, we come up with a density model. That's one way of doing it. Or we look at seismic tomography. Seismic tomography images wave speeds. There's a bit of an issue because If you want to know the upper mantle underneath the plates, you want to look at an S-wave model because it can include surface waves. If you want to represent fine-scale structures around the subduction zones, usually it's better to look at P waves, so there's a bit of an issue, but broadly speaking, tomography images slabs. You can then take this image of relative wave speed anomalies and just use mineral physics to somehow scale it, and Doug talked about this already, to temperature, and all of a sudden you have a temperature map, a couple hundred degrees anomalies, and you can convert that to density. Okay, so let's do this, and let's run a computation that's basically just like the Stokes sphere, only that we've now put in anomalies, in this particular case from tomography, and we can solve those equations, and we can predict flow at the surface of the Earth. Right? This is a model that has free slip. Things can move whichever way they want. It doesn't have any lateral viscosity variations. Does that look a lot like plate velocities? A little bit, maybe? No, not at all. Not at all is probably the right answer, because there's a bunch of things missing, right? So we have localized plate motions. This is much broader, and there seems to be like a whole part of the velocity field missing, and that what's missing is the toroidal field, right? And so what we've done here, because there are no lateral viscosity variations, we've generated a flow field that has only sources and sinks. And this looks like this. And the surface of the Earth, as represented by plate tectonics, has both sources and sinks, and it has this strike slip motion, and it has this wholesale spin. So that goes back to Doug's questions. Here you see this large-scale spin for this particular hotspot reference frame. So we're missing a lot of things, and that's because we have not included the lateral viscosity variations that correspond to the plate boundary. So that's an important ingredient if you want to ask the question about the plate driving forces. Turns out we can prescribe velocities at the surface of the Earth, as done here for a scenario at 130 MA. We can compute flow at depth. We can compute the tractions that correspond to single plate motions. We can then integrate over these tractions and come up with torques that are to do with motion of one plate in one direction on all the other plates. We can redo this in every direction. We can assemble an inversion for plate velocities here in omega vector, given those plate-plate interactions, and a sum over the driving forces, such as due to our sphere that's rising or the slab that's sinking. If we do this particular computation here includes lateral viscosity variations, we arrive at plate motion models where this is the prediction here, that sort of work. Right? So this means, okay, our understanding about slab pull and the whole distribution of density anomalies is pretty okay. It's not perfect. I'm going to get back to this in a second. If we then ask, well, what sort of forces do I need to add if I just take P-wave tomography, if I just take S-wave tomography, or if I use models that are based on slabs that I'm going to talk about in a second? It turns out that the biggest improvement you get really is if you include either slab pull, meaning the force due to a sinker, or slab suction, meaning the force to a plate being pulled from the side, in terms of the correlation here. And this is one important distinction that comes back to some of the issues that are fundamental in subduction dynamics. And so slab pull, as sort of, coined by Clint Conrad and Lithgow Bertoloni, is a situation where we have an asymmetric force transmission, perhaps through a strong slab, and slab suction is one where we have the symmetric sinking, perhaps two limbs of a convection cell and a relatively weak slab. And those two are expressed differently as surface motions, and you might want to turn things around and then say, well, let me use this now, this experiment that Earth has set up, to say something about the relative strength of the slabs. This is what Clint did in Carolina, showing you the plate velocities if you have the weak slab suction only, and if you have a little bit of slab pull on the sides, and they emphasize here the relative speeds of the plates, this oceanic to continental ratio, right? Oceanic plates moving faster. And that's interesting, but it also turns out that if you allow for lateral viscosity variations in the asthenosphere, as are shown here with the colors, that also speeds up the plate velocities, because if you think back at Stokes flow, right, the viscosity is smaller, so you get larger velocities, and this would be a scenario that only has slab suction, no slab pull. So there's a trade-off, and if we look at two different models, one that have no asthenospheric viscosity reduction here in blue, and one set that has different kinds of viscosity reduction, then it takes a different amount of slab pull to reach the observed, the observed sort of 3.4 ratio of subducting to non-subducting plate speeds, right? So you have different answers, right? A lot of slab pull or less slab pull give asthenospheric viscosity reduction. One example of a trade-off between the strength of the slab and the strength of the asthenosphere that complicates the experiment. Right? And we're still sort of trying to wrap our heads around that. Now there are some other uncertainties, obviously, and here's another prediction of plate velocities from Alex Forte, much, much better than the one I showed earlier. And what is done here in this computation is a joint inversion of a range of observations is performed to address this issue. Well, how much of tomography is actually imaging compositional anomalies as opposed to thermal anomalies? And that's an ongoing debate, and what is shown here in a paper by Rowley that talks about stability of upwellings is a cross-section through an upwelling underneath the East Pacific Rise for a simple viscosity model with a simple density scaling, and one and is based on their joint inversion has a more complicated viscosity structure. So just as an illustration that, the Earth model that is inherent to this computation does have uncertainties, and you get different answers in terms of the flow, both for downwellings and for upwellings. Now, how to make sense of this? Well, we have one realization of the experiment for the present day. We can also go back in time, right? We can also query different states of our planet. And dynamics in the past, if we go back further than the Cenozoic, may well have been very different. But if we go back only 70 million years or so, we can assume, well, overall, maybe the parameters of viscosity are the same. We can try to explain plate motions such as the one shown here from Miller, including this super rapid motion of India, for example. What can we do about that? A lot of the work was done here at Berkeley, and some of it goes back to Yannick Ricard, Carolina Bertoloni, and Mark Richards. And so the idea is, well, let's just embrace the fact that subduction zones have moved over time, as indicated here in colors, as trench locations over time, and then use this intuition of a slablet, of a unit of density anomaly that's sinking, to build a density model of the mantle. And let's maybe do that by dropping these slablets wherever the trenches are and slowing them down in the lower mantle because it has a higher viscosity. Right? If you do that, you find that the velocity decrease here between the upper and the lower mantle is a strong control on the match in terms of correlation between your slab model and seismic tomography. That's nice. That gives you one constraint on this uncertain rheology. You can build a model of the present day density distribution of the mantle and the past, and you can then turn the question around and ask, well, how well does our model of plate driving forces being dominated by slab pull work over time? And that's shown here in terms of the correlation with plate speeds given that particular density model. Turns out it's pretty good, except around 43 MA, we have the change in the Emperor Hawaiian Seamount chain. I'm going to come back to this in a bit. But overall, slab pull is really a good explanation for the driving forces. Now, to analyze things on the globe a little bit further, we like to often use spherical harmonics, shown here in the first couple of degrees. Spherical harmonics are global basis functions, including cosines and sines and Legendre polynomials. They basically allow you to decompose things just like an FFT on the surface of the sphere. Degree 2 is something you'll often hear because the order 2, degree 2 pattern has this sort of ring of fire kind of thing, like the subduction zones are aligned right now, and people doing plate tectonic reconstructions like to obsess about the transitions between degree 1 and degree 2, for example. Now here's degree 4, degree 8, you can sort of see how this is going. Now if we then decompose the match of one of those subduction zone models and compare it with a more modern tomography and express the correlation as a function of degree of wavelength and depth, then we find that the match is quite good, but only good at the longest wavelengths. Meaning that if we look at anything shorter wavelengths than a couple of thousand kilometers, there's really not that great a match of any of these models, including those that involve lateral advection of slablets or that involve thermochemical piles with seismic tomography. So we're missing quite a bit here. Now, why is that? And there are a number of reasons why we may be missing something in this forward model of Mantle structure that's purely based on subduction. One is we might just not be seeing the slab tomographically. That's not really an issue. Here's an example where there's an input model, typical global coverage, and here's the output model. It has slabs and plumes in it, and up to degree 15 or so, we should be seeing the slab in a ray theoretical framework. So perhaps not the biggest issue. Another issue, what about mineral physics? This is from a paper by Yannick Ricard, making sort of an extreme end member case, including phase transitions. Here's a thermal model, and here's the density model, and here's a suggestion of what you might be seeing in P waves, and here in sort of imaginary bulk wave speed tomography. So if this is true, then just based on mineral physics, we should be losing a lot of slab in the deep mantle. Right? So there are complexities in there. Another interesting complexity is that if we look at the predicted slab trajectories at depth, we have to remember that those are 3D and that the plate motions are changing. And so if you look in cross-section, you may be missing a lot of things where really you had a coherent subduction zone as illustrated here for the northwestern US, but it may look very choppy in cross-section, right? And so these offsets will be very bad for correlations. Yes?
Sorry, this is going by fast, but so are you saying that you think we should be able to see subducting slabs in the lower mantle if they're there?
Yes, and we should be seeing them.
Given how we're able to resolve
yes.
high-frequency seismic
yes.
images from body waves?
Yes.
That's sort of startling, but okay.
Why? Here's why I'm saying that.
Rays
okay?
bend and things hide from seismic rays pretty easily.
Yeah, but not really, right? So when you look at some of the tests, right? For instance, some of the tests of plumes, then those are usually set up in a way that wavefront healing and stuff like that makes it very easy to hide them. But then if you explore different ray path coverage, right, it turns out that you may be able to actually see some of the plumes. And then what I'm talking about here is a degree 15 representation.
Are you relying on slabs being thickened in the lower mantle, as in sort of folding up rather than being on the order of just 100 kilometers thick?
Correct. So those are relatively fat slabs, right? And this is saying if the slabs look something like that, which is a representation of our forward models. So if the slabs look like what they should look like if we account for diffusion and the transport of these slablets.
Thorsten, does the velocity only depend on temperature?
In this particular case, for simplicity, yes. But that was one of my slides, right? So we may be not seeing them because of composition, for example. Right? And so yes, I'm saying that up to degree 15, I expect things to show up, and we're not seeing them. So we're missing something in our forward models.
Thorsten, the correlation diagram that you showed there was from 2001. So how does that look with modern tomography?
Doesn't look much. The tomography doesn't change things at all, basically. The geodynamic models have gotten a little bit better, but not much better. I think this is a real issue, and if you don't believe this argument, then show it.
Well, maybe we'll have some time to work through this, because I'm trying to understand how at degrees less than 15 you can see, features that are a couple hundred kilometers wide or thinner, which is sort of what I would
I just
expect.
explained, right? This assumes that the slabs are wider than that.
So, but they need thousands of kilometers. I guess I'm sort of confused what this test really is. I mean, are you letting these slabs smear out to sort of thousands of kilometers wide, or?
Well, this is showing you what the slabs look like in this particular test.
So, okay, think about it.
So my point is that our geodynamic models are good enough to create structures of a scale that tomography should see. Tomography does not see these structures, therefore something is missing.
Could you just remind us of what the wavelength would be for degree 15?
Circumference of the Earth divided by 2 divided by 15. Right? We're still talking about very large scale structures.
Yeah, hundreds of kilometers.
Yeah, for sure.
Right, about 1,000.
Yeah.
I mean, it's always a little bit difficult to make arguments based on not seeing something. Because, I mean, you can imagine many ways that seismologists could fail to see something. I mean, we admit that.
Thorsten, you're not saying that there's a problem with the seismology, right?
No.
You're saying there's a problem with the geodynamic model.
Absolutely. Was that the problem? Come on, guys. You're not that stupid, right?
No, but I mean, he's making the argument that because he's throwing away geodynamic models because we're not seeing things.
No, I'm not throwing them away. I'm suggesting ways for improving them, right? And I'm suggesting why, for example, Magali's talk that's dealing with the issue of slabs going through 660 is really important. Because even though this is a long-standing issue, we haven't resolved it. And I do believe that if we make progress in the plate reconstructions and understanding slab mantle rheology and what happens with the mass flux at 660, that this sort of correlation should improve. All right, this is my argument, and I'll stand by that. And I think the reason is a complicated one, because the plate reconstructions to some extent depend on our understanding how slabs make it through 660 and vice versa. And it's never quite clear what to blame. Is the plate reconstruction wrong, right? Are we seeing something like this here, and we don't have the kinematics right? Or do we not understand how the slab sinks through 660? But it's a way to make progress. And I think I'll stand here and I'll claim that we do not understand slab flux through 660 until we've improved the match here to a level that's better as to what we have now, to a level that goes from 10,000 kilometers to 1,000 kilometers.
So, Thorsten, do you think if you show that correlation plot again, how important is it that you're missing the shallow structure in those like 6 to 9?
Right. So this is another thing that can be addressed, for example, which is why I showed this thing here, which is work by Bauer and Gernes and others, where they've prescribed the trajectories of the slabs in the upper mantle. Because we know that slab morphology in the upper mantle is quite complex, and it doesn't come out that way in our forward prescribed geodynamic models. And so it's important, but that part we could assimilate, we could fudge, right, by prescribing the trajectories based on the Waddachi-Benioff zones, for example. Matt had a question.
You started your talk with Newtonian viscosity.
Yeah.
Is that correlation still based upon Newtonian rheology?
Yes, for the most part it is.
Okay.
And that will definitely change things. That could be one answer that we don't, and I'm going to comment on that in a bit.
Right.
It could be part of that, we're missing the nonlinearities in the upper mantle of viscosity.
Okay.
Absolutely. Other questions? So yeah, I think this is a real bummer and an opportunity. And if the seismologists are telling me that really we shouldn't worry about anything larger than degree 9, then okay. Right. So other constraints. Right? So we already know that these forward models based on slabs and plate velocities are not giving us the whole solution. Another thing to look at is the geoid. A geoid is the equipotential surface of the Earth, would be coincident with the level of the ocean at rest. And we can distinguish it from dynamic topography, which is the reflection of the, say, the surface, the top part of the mantle and the core mantle boundary due to internal loads. And again, if we want to make progress here, we think about Stokes flow, and these Stokes flow anomalies will cause a deflection of the dynamic topography, which corresponds to density contrast and will lead to an undulation of the geoid that is shown here in this sort of stupid little rotating movie. Now, because the geoid is a useful thing, right? Because it depends, for the most part, on the stresses rather than the velocity. So it provides a complementary constraint to plate velocities. It's useful to appreciate what the actual datum is. And as it turns out, in many cases, if you're trying to fit data isn't actually data, but a model, and the geoid is no different. And so here's one way of looking at the geoid. It's not actually the geoid. It's the ITG Grace geoid taken out the ellipticity of the Earth. And if you don't do that, the Earth is sort of this egg-shaped, right? It's not really an egg, whatever. Then you don't see anything but the equatorial flattening. The amplitudes here, hundreds of meters, are quite small. So what I've done here, which is often done, is I've taken out all ellipticity, right? And this is then what it looks like. You get this blue ring, you get some red stuff. This is not the only way to do this, and this is perhaps not the best way of doing it, because even a homogeneous Earth that is spinning will have an ellipticity that is different from 0. And so if you're asking what is the dynamic contribution due to the Stokes sinkers and risers, you might want to take out the hydrostatic correction, and this is what it looks like. So see, this is quite different. The negative anomalies fall to the poles, which is probably where they should be, and the anomaly that's sitting over India is much less pronounced. This goes back to one correction. Fairly recently, folks have worked through the math again and have come up with a different correction, and that doesn't look much different, but if you're going after the subtle long wavelength fits, this may or may not have sort of a 10% effect. So really, we should be looking at something like that rather than something like that. Another intriguing thing is that the geoid and the gravity anomalies are the same thing, because one is just the derivative of the other. And so they contain the same information, but if you choose to fit the geoid as indicated here by its spectrum as a function of wavelength, or if you fit the gravity, then you will have a different bias of long wavelength compared to short wavelength structure. And so depending on what you choose, you're sensitive to different parts of the power spectrum. How do we go about fitting the geoid? And this goes back to things that Mark Riches, who's in the audience, and Brad Hager worked out. I'll see you on the car. This is a figure from Magley Bill's talk a long time ago. So let's consider our Stokes anomaly. Just based on density, if nothing happens, the geoid should have a positive deflection because we have to move further away from the density anomaly to feel the same gravity. If we include the flow part, then this flow will suck down the surface, and the dynamic topography plus density effect is such that the total is slightly negative. We can express this as kernels, where for this particular Earth model in terms of viscosity, I'm showing you the geoid effect, surface topography, and CMB topography effect based on a density anomaly at a certain depth and wavelength. It's all negative because things are being pulled down, and the longest wavelengths in the mid-mantle are most important. And our fundamental finding is that if you then include a lower mantle viscosity contrast, that signal flips sign. It flips sign because the effect on surface topography of deep mantle anomalies is reduced, and you have a reshaping on the effect of CMB topography such that the combined effect says that if you're in the mid-mantle at the longest wavelengths, you actually have a positive effect on the geoid. And so illustrated here, if we put our tomography again in this free slip computation from before, we predict the geoid for homogeneous mantle. Doesn't work at all, really. We just see the poloidal field, basically. If we have an increase in viscosity in the lower mantle, we get this flip in sign over the subduction zones. And if we have some sort of 4-layer model, we can match the observed geoid fairly okay at a fairly high correlation. So that's nice because it gives us some constraint on the bulk viscosity of the mantle that we already know will have an interaction with the viscosity of the subduction zones. Now the problem with the geoid is, again, it's non-unique. This is from work by Panesuk and Hager showing, based on the Monte Carlo approach, there are different families of viscosity in terms of the behavior with respect to depth that can match the geodynamic topography equally well. And that's a bit of an issue because it then... That's orders of magnitude, so this would be 10 to the 21, sorry about that. This is 100 times stronger, 100 times weaker. Sorry. So basically, some low viscosity in the upper mantle, maybe 10 to the 19, and some increase, but with a lot of flexibility as to the amount of that increase. Now, there is a range of viscosity inversions. For instance, this one here by Forte and Mitrovica does include other constraints such as some glacial isostatic adjustment that I cannot really talk about now. But in terms of global dynamics, one of the things that hasn't happened is that the ice load models that were derived do not always or almost never have the same viscosity as the sort of viscosities you arrive at when you fit the plate velocities or the geoid. So there's a real need for improvement there. Coming back to the slabs and the...
I've been wondering about that for a long time. Why is it that there's no convergence there, and what can be done about that?
Politics. And access to data, and the fact that the...
Besides, like, ignoring healthcare.
That's the problem. Not, because I'm on camera. And I don't know that, but there's a real, I think, there's a bit of a lack of communication between the communities that worry about the geological markers and the ice models and the ones that do the joint inversions. But I think this is a true statement, and people working in the fields are aware of it, and they're trying to address it, but it's a real issue. Another issue, of course, being that a lot of the ice load constraints come from places where we might have strong continental keels underneath it, so we may be biased in that. Another issue that we have been looking at different timescales. Yes?
Thorsten, I'd go a little, is this on? I'd go a little easier on the geodynamicists in this case. The geoid models and the post-glacial rebound models have very little resolution of radial viscosity structure, even in an ideal world where there's very little lateral viscosity variations. But there's a trade-off between the cube of the thickness of a layer and the viscosity contrast, and it's unresolvable in both studies, both types of studies. And yeah, the data sets are different. They have different kind of wavelength characteristics. But really the only thing we know from all these models put together is that the upper mantle on average has probably 1 to 2 orders of magnitude lower viscosity than the lower mantle. It's not likely to improve because extending that globally is almost meaningless in the face of large lateral viscosity variations associated with continents and thermal variations and so forth. So I don't mean to be too pessimistic. I'm actually I think we should move on. I don't think the geoid and the post-glacial rebound models are going to tell us much more about this problem.
I think I would mainly agree with that statement, with the caveat that folks are trying to come up with consistent descriptions, for example, of the oceanic lithosphere underneath plates, which are in places not unaffected by the response to post-glacial rebound. And you already know that you cannot build a consistent model because you're off by orders of magnitude. So I think it would be of value to have a simple first order model, just as the one you just alluded to now, and have an ice model that's consistent with that. And we don't have that.
As long as we don't take it all too seriously.
Absolutely. Other questions? And so in terms of the regional dynamics, the viscosity structure is not something that's just interesting because you're trying to build a consistent Earth model, trying to match the geoid. It's also something that will very much affect how slabs make it through the transition zone. And Magley is going to talk a little bit about this, and there's been a recent debate as to if that increase in viscosity should be at 660 or at 1,000 kilometers, and here's an example from 25 years ago, suggesting that maybe this is a plausible viscosity structure, and we still have large uncertainties. But whatever you come up with in terms of a constraint of viscosity with depth, it should be consistent with what we observe as to the complexity of slabs making through 660 or not, right, or ponding in different places. Now, one of the things that I think that can help us with that are less explored than the geoid and the plate velocities, for example, just as an illustration of the other constraints we could look at, are the global distributions of focal mechanisms. And this is an observation that goes back to Isaacs and Molnar, at least in '71, is that when you look at the in-plane extension for different subduction zones, Waddachi-Benioff zones, then for the most part, they're extensional at the surface and they're compressional at depth. And we can plot this in terms of an in-slab projection, where again the color is extension, compression. You can see there's some complexity as to slabs are being deformed, where they're being squished less and where they're being squished more. We can run models, such as this one here, that's a global circulation computation that includes those viscosity changes. This goes back to Vasilio and Hager, lots of work by Alisic and others, Mike Gurnis's group. And we can try to match this structure, and we can make sure that the viscosity increases and the impediment to penetration is consistent with what we're seeing at the strain rates that are imaged by focal mechanisms. I think we can explore this more. So I want to talk a little bit, last half hour, about regional models and then bring it back to the global scale. So given these complexities, right, and given we heard that post-glacial rebound estimates may be biased by lateral viscosity variations, we know that local tectonics matter. And so this is telling us that the Earth doesn't set up perfect experiments, right? So therefore, why not set up our own experiments where at least we have the control over these parameters and we can try to extract some rules before we then go back and look at the zoo of subduction zones globally. And so there's a long history of these models, and here's some seminal work by Uli Christensen showing you, for example, when you push things and the slab goes through 660, then the behavior as to penetration through 660 or as to ponding on the 660 phase transition is very much controlled by the trench motion, which is fast here and which is slow in this case. Another important control is what is happening at the phase transition. And the main effect here is that if you have a phase transition, you go from lower to higher density, and the behavior in temperature pressure space is governed by a slope. If that Klapper slope is negative, then the phase transition will be depressed downward in cold material such as a subducted slab, and this will serve to push things upward. And Magali is going to talk more about that. And so if that phase transition is strong, you will also have an issue with penetration. Right, so we know that trench rollback is an important parameter, not the only one. Slab strength is another one, and Magali is going to talk more about this. And so this motivates then a lot of work as to trying to understand how this trench is moving, right? If we don't want to push the trench, and I try to focus on dynamics here, then let's figure out the sort of inherent system behavior as a function of simple control variables. There's been about 100 papers on this sort of thing. And here's one example from laboratory work, and Claudio Ficena is going to run a tutorial, I think, which is pretty ambitious, on setting up experiments like that. And this is showing you that as a function of the normalized Stokes velocity, which is something like a density contrast, and the strength of the slab, you go from rollback of the trench to advancing in this intermediate scheme and then to retreating again depending on the bending strength of the slab. Here's another diagram from Dave Stegman based on numerical work showing you again that based on density and some sort of stiffness of the slab, you get different regimes, right? And so if that's true, that's nice because then you can look around and look at these different experiments and make inferences on the slab strength. If you have better slab strength, maybe you can improve these large-scale models. Now, there are some annoyances, and some of them turn out to be perhaps a little bit more important than we thought 10 years ago when we set up these isolated models. For one, there's an overriding plate, right? This is maybe not a surprise, but it seemed like a good idea at the time to just look at isolated plates. Maybe not such a good idea. Basically, the problem is that if you have an overriding plate, you change the boundary condition from free slip to no slip, and the Stokes system feels the boundary conditions from far away. You slow things down. And this is illustrated here in terms of different velocity components. You just get different dynamics. It's somewhat straightforward to capture that. But the overriding plate matters for a number of other reasons. And so the overriding plate then turns out to have a control on those systematics of having folded slabs or having inclined strong retreat. And it's not just the subducting plate, but it's also the overriding plate that seems to control what's happening. Well, why is that? Well, one of the reasons is that, okay, so this is one annoyance, the upper plate. Another one, this is coming back to your question as to the nonlinear viscosity. We can never really isolate the dynamics of the system without accounting for the potential feedbacks we get if we were to employ something like laboratory-derived rheologies for olivine. This is illustrated here in a very simple model showing you a Newtonian system rolling back quite a bit. And here's a non-Newtonian system, similar to work by Magali and Margaret, where the viscosity gets reduced by the strain rates, and you can see this acts to lubricate the slab and makes it much more stationary. So if you use the rules from Newtonian viscosity for plate reconstructions, as some people are doing, you may be off if you neglect that effect. Now let's look a little bit more at the plate itself, about the plate rheology. And that comes back to the effect of the overriding plate. Recently, after the Tohoku-Oki 2011 event, we had an interesting experiment where this large earthquake loaded the upper mantle on length scales that are comparable to the length scales we're addressing in these tectonic models. The time scales are still way off, but we can query the post-seismic deformation as imaged in GPS and infer equivalent viscosities, which is done here. And so what we then find is that there's a mantle wedge with some plausible viscosities, and we find this interesting weak lower layer. As Mark said, we have a very hard time saying something about the thickness of the layer with respect to its strength, but one solution is a fairly broad layer that has a viscosity reduction that seems to happen in the depth region where piles creep. Low temperature creep may affect the temperature-dependent viscosity of the plate, and so this is very interesting, and what this means is that we're seeing some plastic weakening, and that this plastic weakening may reduce the bending strength even in the lower part of the plate. Now, another piece of evidence that a plate might be affected strongly by plastic deformation comes from a reanalysis of this global set of this ensemble of subduction zones in terms of the relationship between overriding plate thickness and bending radius. It turns out if you have a purely viscous plate, like the one I showed earlier, the overriding plate should have no control on the bending radius. If you have a plastic plate that is weakened by piles creep in the way that was pointed out in that Christmas tree diagram by Bruce and myself, and in a way that we found from post-seismic deformation, then that plate will be more sensitive to what is happening at the interface, and that plate will respond to the overriding plate thickness. If we look on Earth, we have some sort of way of measuring overriding plate thickness, and there's a fairly nice correlation between the two, which would also argue that plates are behaving effectively plastically. Right? And so what this may look like is shown here, where there's a simplified computation with plastic reduction in viscosity here. This is relative to 10 to the 21. Or there's a more complete one by Garel and others showing you what the viscosity may look like for different deformation mechanisms. And so it's possible, it's not clear, but it's possible that the slab may be even weaker than many of us thought, and maybe something like 100 times stronger than the upper mantle if this plastic weakening is true. Yes?
Are you using plastic and pyres synonymous?
Yes, here in this case, yes. For simplicity, and here this has another plasticity built in and piles and another yield stress. So I'm just saying there's an indication for viscosity reduction. That viscosity reduction reduces the bending strength. If that's true, then we can go back to trying to divvy out how the viscous dissipation, how this part, right, this derivative, the sum of derivative of the stress tensor, divvies up into different parts of the system. This was pointed out by Clint Conrad that you can also get at a balance of plate velocities by looking at the buoyancy forces due to the slab pull, the dissipation within the interface, the dissipation in the convecting mantle, and the dissipation due to slab bending. And for a long time, we thought that this is a fairly small term, and this is the thing that dominates. But if plasticity or some other weakening mechanism operates, then this will be fairly small, and these other terms matter. In particular, this implies that the subduction zone interface may matter. Here's an example using rheologies, creep laws for eclogite, having basalt coming into the thrust interface, and here's a quartz diffusion creep law and temperature viscosity space, as you might expect if you have sediments coming into the creep law. And just using this force balance for simplicity, you can then look at the plate velocities here as a function of shear zone viscosity, and if you pick these numbers and temperature conditions, that you may have in a subduction shear zone, then slabs that have a basaltic interface may move much, much slower than slabs that have a sediment lubricated interface. This may be all nonsense, but the force balance tells you that the interface may be quite a bit more important than we thought. And this means that geology may matter, which is of course horror for a geodynamicist, right? Where we like to have everything homogeneous. But it also, again, gives you some avenue to test this in way forward, because you can only have sediment lubrication, presumably, when you have continents. So for Earth evolution, this may actually tell you something. But just an illustration, for those sort of values, the interface may matter. Yes. All right. How many slides do I have? Yes.
Yeah, so just to clarify, to make sure I understand, so the viscosities you're showing there on the left would be for the interface.
Yeah.
And that would be depths that would be somewhat deeper than the seismogenic.
Correct. The seismogenic zone would not matter here. This is a
Right.
shear interface at depth.
Yeah, okay.
And
Gotcha.
the depth here, this is controlled by the thickness of the overriding plate, which we've, in this particular case, taken from the scaling relationship you get from the plastic slab.
Okay, and then so for those sort of viscosities, if you're looking at the shallow end of the area you're talking about, what's the stress for, let's say, constant creep compared to, say, an earthquake stress drop?
They would be higher, but not insanely high, something like 50 MPa. So in the high end of earthquake stress drop.
Okay, thanks.
But this would be just talking about the shear zone.
How deep does your, upper frictional sliding or decoupled region go?
This is assumed to be a fairly small stress based on sort of, seismic observations. This has I think this is a fixed number here, and this will be controlled by the overriding plate.
So, does this conflict then with what Peter was saying about like 80 kilometers deep?
That would be this part here.
But he's considering it all to be decoupled. So,
yes, this would have significant shear stress. Correct.
Do you really expect the project transition to be that shallow?
This is factored in, so the depth ranges are supposedly okay, given the temperatures that are estimated from the computations. So there might be an inconsistency there in terms of the temperatures, actually. Yeah. This is true or not, this is just an illustration that whatever is happening at the interface may have a strong effect on the plate velocities. All right, and so coming back to how things work, and Doug had alluded to the work by Wei and others before. I think for figuring out what's happening in the bending region, it would be very interesting to also look at the strain rates that are predicted by these geodynamic models and consider things like the double seismic zone, where we have compression on the top here shown for one slice along Japan and extension at the base, and particularly what happens here inboard to see if there's some indication in terms of the style of strain release and the rate of strain release that would help us to understand what's happening with the weakening, and not only those bulk effects that I mentioned, but also the weakening by means of fluid inclusions and faults and so on. And so we're going to have a complex interaction here between the volatile transport, of course, and the mechanics of the system. But I think this sort of thing is underexploited, and it's complicated, of course, by the fact that, again, we're looking at different timescales, and you have to make sure that you're not offset by what's happening throughout the seismic cycle. All right, so what are the things, the other things we can look at? Well, one is slabs are not alone, and we can look at slab-slab interactions, and here's just one illustration of what the pressure field does if you have two slabs that are subducting. And those, and this is something I discussed with Margaret yesterday, if we have a three-dimensional system, then sometimes the pressure distributions due to slab interactions can be non-intuitive and can lead to modifications, for example, in the rollback behavior you would have inferred from an isolated slab. And so here's an example of that, showing you one slab coming in behind the other. If it were a single case, then the slab would roll back. If it's this coupled case, then there's a force transmission, and the trailing slab actually changes into an advancing mode that you would not have predicted based on the rheology of the slab alone. And we're not just studying these two slabs because next week we're going to do 3 slabs and then 4. It turns out that the pressure variations that are induced by 2 slabs are of a more extreme value, and they help us to understand single slab dynamics. Now, another issue with this is that if we're looking at things like trench advance and trench rollback on Earth, shown here in one particular reference frame for the Japan system, where this trench is inferred to roll back, this one is inferred to advance, then this measurement is contingent on the global reference frame, the thing we discussed earlier. Right? And so you need to pick an absolute reference frame, which is mainly controlled by its net rotation. The net rotation itself, as illustrated here by a static computation by Melanie Giraud or a dynamic computation by Xi Zhang and Mike Kernels, is something that has global interactions. Right? We need to make sure we account for global slab interactions to understand regional force transmissions, such as the advance and retreat, and that may well affect what's happening at the thrust interface, perhaps not unimportant for the sort of distribution of seismic coupling and where we have megathrust earthquakes or not. So it's a across the scale problem. Now slabs, obviously, in terms of plate tectonics, are not the whole story. And depending on where we are in the planet's evolution, depending where we are in the partition in between up and down wellings, we expect other contributions. One way to look at this is to again consider the temporal sampling that plate tectonic reconstructions provide us. One thing to do is to look at the Pacific. If you look at the Pacific over the past 70 million years or so, then you can work out the sort of force or torque that's exerted on the Pacific based on where the subduction zones are. You can compare the direction of that force very simply with the velocity direction that the Pacific has experienced, and that works fairly nicely back to 60 MA. But at 60 MA, you have no more attached slabs, and the Pacific plate is still moving quite happily. Right? So something else must be propelling the plate. It's not just slab pull. The other part of the puzzle are plumes. Right? Plumes are interesting. We can try to predict where plumes are. We can try to predict plume conduits, such as what Bernhard Steinberger and Hassan and others have done. And one of the perennial questions is, well, has the plate moved or have the plumes moved? And recently, the pendulum is sort of back, according to Torsvik and others, in that the plume has moved, and there's a little bit, but there's a change in plate motions, explaining this Emperor-Simon bend that I mentioned earlier. Now, if we look at the forward models of these plumes and where the conduits are, then it turns out that the correlation between the slow velocity anomalies inferred at the conduits and seismic tomography is actually better than with any of the slab models. Right? And there is now a real one for you, right? Because plumes should be really thin if they were thermal. There should be no reason for tomography to see them, but perhaps if they're thermochemical, as others have argued, including Barbara and the Princeton group, we should be seeing that. But just on face value, doing the same correlation analysis, right, the case is much stronger for plumes in the lower mantle, continuous to some hotspots, than it is for slabs. Just something to mull over. Now, in terms of driving forces, plumes have a harder time of driving the plates because they're not attached at the edges of the plates, typically. This is illustrated here. 2 density sources expressed in terms of the poloidal flow field if the Earth didn't have any plates, and expressed in terms of plate motions. And here, this particular density anomaly just sits underneath the plates. The tractions average out, so you get very little motion. This one happens to be underneath the East Pacific Rise, and you get nice plate motions, right? And so plumes are not really a good driver of plates. They may prime plates in terms of modifying the lithosphere and make them move faster, but broad upwellings are much better way to drive plates. And so we think that, for example, at present, there are these large-scale systems of mantle conveyor belts, one being an upwelling underneath the African swell that's connected to the Tethyan slab, another one being an upwelling underneath the Pacific that's connected to the Cordillera, the subduction underneath South America. And so you can then wonder about the relationship between the cold downwelling limbs and the hot broad upwellings that are perhaps related to those. And so we made the case, for example, that at present India may be driven by one of those conveyor belts because there's no slab attached. And in the past, perhaps India was propelled at these rapid speeds because we had 2 slabs attached, right? So we're trying to divvy this out. But the important part here is not if we're right or wrong. It's to illustrate some of the things, coming back to what I said earlier, as to the potential links between the record of subduction and the oceanic plate system and what is recorded in the continental plates. One way to look at this is to go back to this dichotomy, perhaps, of slab pull versus suction, where I explored this earlier in terms of slab strength, and think of it as something that's changing over time, where slab pull force transition may be associated with a slab ponding at 660. Once the slab goes through 660, establishes a large-scale convection cell, perhaps also triggers an active upwelling, you're moving toward more of a slab suction scenario. If we're trying to find a record of that at the surface, this may be associated with relatively little shortening, and this may be associated with large-scale shortening, so a more larger-scale orogeny. We suggested that if you try to trace back anomalies in the mantle, going back to 60 million years, then the Deccan traps and the penetration of the Tethyan slab at around 60 MA may have been associated with the establishment of this large-scale conveyor belt and the large-scale collision in Tibet. Another place to look at this, where we might be seeing a spatial progression of slab penetrating through 660, is along South America, looking at the Andes, Cordillera. Then when we go from north to south, it appears that the slab goes through 660 in the north, sits on top of 660 in the south, and there may be a correlation with the timing of onset of shortening, where the onset of shortening and mountain formation in the north was earlier than it is in the south. If this is true or not, I think it's really worthwhile to explore ways of trying to link the progressive evolution of the convective system with whatever may be recorded in the continental plates, because those have a longer memory. We may then be able to read planetary surfaces in terms of the deep dynamics. Now, I want to end with a couple of words on the mantle convection part, because for the most part here, I've just talked about circulation, how to query different data sets. And so we take the equations from before, but importantly, we have to realize, right, we need to conserve energy. So we're introducing an advection term, the balance between the two governed by the Peckley number, and perhaps a heat generation term, and this is telling us how the energy changes over time. And one important point about this is that the degree of heating, the ratio between the basal heating and the internal heating, will control the relative importance of those two players, hot upwellings and cold downwellings. And this is something that will change over Earth's history. And if we're trying to think about subduction a couple billion years ago, assuming that something like plate tectonics happened, then we will have a different partitioning, right? And here are the extreme cases, purely basally heated, purely internally heated up there. If you're purely internally heated, you will only have cold downwellings. It turns out it's much easier to generate plate tectonics this way, and a lot of the plate generating models you'll see are basically formulated like that. As Koranaga recently pointed out, this was nothing new, but it's a nice review paper, is that if you then go from the isoviscous case, and you break the symmetry, and you induce temperature-dependent viscosity, and you then have mixed heating and yielding, then the same heating state for different yield parameters will give you very different pictures in terms of the temperature, right? Obviously, we know that for strong yield stress, we are in a stagnant lid regime. For weak yield stress, we're somewhere in this sort of squishy convection regime, and somewhere in between, maybe we're plate tectonic-y, right? But this sort of relationship then may have changed over the history of a planet. And whatever we're thinking about the importance of subduction right now may not be true in the past, and we have to be very careful in trying to think about other systems, in particular exoplanets, and that heat production and yield stress surface tectonics are linked and will determine what's happening in the interior. And so in closing, one of the amusing things that occurs to me is that when we have this sort of mix between downwellings and upwellings, then we're talking about large-scale structure in the mantle. One of my sort of least successful papers was this suggestion in '99.
Beautiful.
Thank you, Peter. pay you later. But I'll be vindicated, right? So I'm just pretending to make deprecating comments about myself. Just wait. But what we did is we took Michael Manga's experiments that suggested that if you have high viscosity blobs, then those will tend to go to the center of convection cells because the strain rates are lower, and this may be a way to hide geochemical reservoirs. And that sort of thing has recently been rediscovered on some level by Balmer and others, where they're calling these blobs beams, and the idea is you have bridgemanite having a higher viscosity than the surrounding mantle. And that's an interesting suggestion because, for one, it helps with the geochemistry, as we had pointed out earlier, but there are many other dynamic implications that we never thought about, particularly we didn't have mechanisms. But what Balmer suggests, for example, is that these beams may well affect the long-term stability of the conveyor belts, and they even attempt to identify certain structures here that may be centered around lower mantle heterogeneity. So just to note that even in this sort of simple convective understanding of the mantle, there are a lot of fundamental uncertainties that may or may not pan out to affect the subduction dynamics, including on the surface. One reason why this may not be totally crazy, and this is my last slide, is recent work by Yang and Gurnis, where they've used large-scale circulation computations, just like the one I explored earlier, and they've asked the question as to the temperature dependence of viscosity in an inverse sense. And they try to invert for a bunch of stuff, but in particular they have a formulation where the viscosity has a temperature dependence here, E, and if they invert structure and the geoid and what have you, they find that the lower mantle actually appears to have a negative temperature dependence of viscosity. This doesn't make any sense unless there's something but temperature, such as the viscosity of those beams or blobs affecting the structure. And if that is true, then we have to sort of revisit, for example, what happens when slabs impinge on these blobs and what that means for heat transport. So in closing, I basically tried to make a few points about the fundamentals. If you don't take anything away from this lecture but the Stokes velocity and diffusion timescales, that's okay. But I leave up my conclusions here so that we have time for a few more questions. Thank you.
Okay, thanks, Thorsten. So the first round of questions will be from students and postdocs. So Sean.
Thank you. I have a question about mental discontinuities. It's not particularly for your models, but more general for the whole community. It seems, well, some of your models consider 660, some others consider both 410 and 660, some others even ignore it all. To me, it sounds like very random to choose any one, but as a seismologist, I think those are very clear. There are at least two discontinuities, and of course, those properties are poorly constrained probably, but we know there must be some density contrast, viscosity contrast at those depths. But why sounds like the choices are very kind of random and depending on different groups, different
yeah, the choices are not random, but it's a very good point that there are different levels of simplification. For the dynamics, there are two things that matter, as in the Stokes velocity. One is the density contrast, right, and one is the viscosity change. Now, the density contrast factors in, for example, for the sort of 660-ish transition by means of an effective Klaproth slope. Right? And we've seen, as Magali is going to discuss, I think, later this afternoon, that initial choices of the effective Klaproth slope for 660 were misguided, making it appear more important than it may well be if you include other phases and things like that. So it really comes down to what you think the effective Klaproth slope is for every single phase transition. Now, for the ponding of slabs, it turns out that a lot of things can be explained by an increase in viscosity alone. So you do not necessarily need to invoke the negative Klaproth slope for slab stalling for the most part. It may be that you need both, maybe one is good enough, just empirically. Now, in terms of the simplifications, right, this means that if you're missing a phase transition that has a large Klaproth slope, then that's a bad idea. you should put it in. If the Klaprower slope is close to zero, then it's not a bad simplification. And Magali is going to talk much more about that. And I've just not discussed it because I didn't have time. Now the other point is the viscosity change, right? If we associate a viscosity change with the phase transition at 660, it's mostly sort of empirical or ad hoc. We don't really have a good understanding how things might change. Maybe we know what bridgemanite is doing, and so that gives us a better handle for what we should be putting in there. And so in terms of the association between a phase transition and a viscosity change, so many bets off. Now, mid-mantle scatterers, just one comment, I think are very important because they tell us better than tomography as to where slabs might be ponding. So I think mid-mantle scattering is a very important constraint. But you had another question. No?
Well, I just want to directly ask you why you ignored 410.
Oh, the 410? Well, the 410 helps, right? It pulls things down, and for the most part, it'll be just like a colder slab.
Yeah, but still, like, I guess the result won't be changed too much, but you still don't put it in your model, right?
Well, it's not like no one puts it in, right? So I think if you want to do a good job, for example, with the focal mechanisms, you should put it in, right? There are certain problems where you should put it in. But here, in say for the global computations, people have explored the effect of the 410 and the 660, and they're fairly small. And they're really sort of almost lost in the noise of the assumptions you make as to the velocity to density scaling or the assumptions you make about the slab structure, right? So I could now, in my broad view of uncertainties, I could almost subsume them in the uncertainties on the density. Because for the most part, that's what they're doing.
So just a follow-up question on that. What about metastable Aldrin across 410?
Yeah, that will affect the local dynamics, right? And that's a case where it's where you need to know the history to get at the density anomalies, right? So that's a complication, but I think Magali is going to explore a whole lot about that. I mean, my point is not that the phase transitions are not important. I wanted to focus on the large-scale approaches that give you a first-order feeling for what's happening, assuming that Magali and Peter are going to talk more about the phase transitions. And I also don't like phase transitions.
Okay, other questions by students and postdocs? Okay, questions by senior people also. Yes, Louis.
I'm not sure if it's a question or a comment, but one of the things that's quite interesting and was sort of hidden a little bit in some of the things you showed is the interplay between phase changes and things like recrystallization or changes in the grain size. And you could see in some of your viscosity inversions that you showed that some of them have extreme values of viscosity change associated with the phase changes.
Yes.
And I remember Slava, of course, was fascinated by these big lumps in the mantle being large grain-sized domains and stuff like that.
Yes.
And so there's an interesting connection between phase changes and dynamics that
absolutely
might be worth exploring in this whole phase change story.
Absolutely. There are interesting dynamic interactions that will not be captured by the things that I just talked about. And I think Louis was talking about some of these things that were associated with transformational superplasticity. And they do interesting things because they also allow the upper mantle to decouple from the lower mantle. And if you do not want mass transport and you want to have a cold thing on top of a cold thing, then it induces a lot of shear, so you better reduce the viscosities in between. So this is an interesting scenario. And then I didn't talk about any of the time dependence of viscosity much. I mentioned grain size, right? But grain size is something that's not going to be constant. It may have some average, whatever that means, and it will change over time. And that's going to be very important, people think, for plate boundaries, but also for the upper mantle. And so you're going to have a different viscosity, perhaps, underneath a spreading center or a subduction zone. And but some of the numbers I mentioned are consistent with laboratory creep laws for meaningful grain sizes of millimeters or so. So in terms of, I tried to give you a picture of the bulk behavior of the mantle that's not necessarily inconsistent with grain size dependent viscosity. That wasn't Louis' point, but just an aside.
Yeah, I think this is very quick, but I think you mentioned this before, but the reference viscosity on this particular figure, 0 is 10 to the 21?
Yeah, and so the motivation for that is the Haskell constraint, which is based on post-glacial rebound, and it's telling you that roughly when you average over the top 1,200 kilometers underneath places that had ice cover, you end up with something like 5 times 10 to the 21. And so that means that, you know, you can get all kinds of excursions as long as you match the viscosity there. Now recently, thanks to earthquakes in the oceanic, in the Indian Ocean, and in Japan, we've gotten the first sort of constraints on a sub-oceanic plate asthenosphere from geodesy. And they then again are mainly sensitive to relative changes, and they tell you that the upper mantle viscosity is about a factor 100 lower than that, but it would still be consistent with the rest of what I said.
Right, yeah, I was just gonna also point out that earthquake post-seismic studies are, you know, another, at the time of that paper, there wasn't very much information from that, but today there was quite a lot to help control the depth, at least the shallow part of the system.
Yes, it should be, and this trade-off, by the way, that I mentioned earlier with wherever is it, this thing, some of the thinner and weaker scenarios should relax over the next 5 years or something like that. So that's interesting.